All right, everyone, welcome back to The Explainer. I'm your host, and today, we're turning this session into a full-on virtual physics masterclass. So grab a seat and let's dive right in. We're looking at Kepler's laws of planetary motion, basically your complete guide to understanding the actual mechanics of our solar system. Have you ever just looked up at the night sky and wondered, why don't planets just fly off into the dark void of space? Or, for that matter, crash directly into the blazing sun? I mean, why does Earth perfectly and predictably return to the exact same position every single year? To crack this astronomical code, here is our lesson plan for today. We'll cover 1. The planetary motion mystery, 2. Orbital mechanics 101, 3. Kepler's 3 powerful laws, 4. Applications and myth-busting, and finally, 5. The final takeaway. All right, let's kick things off with part 1, the planetary motion mystery. Think about this. Before we had space telescopes, satellites, and supercomputers, the night sky was literally the ultimate puzzle for humanity to solve. And our understanding, it had to evolve dramatically. Way back in the ancient era, Aristotle was absolutely confident that Earth was the center of everything. Fast forward to the 16th century, and Copernicus correctly put the sun at the center, which was a huge step. But he still thought planets moved in perfect circles. Enter Tycho Brahe. This guy made incredibly accurate observations of planetary positions, and get this, completely without telescopes. Johannes Kepler then spent years crunching Brahe's raw data and finally realized, wait a minute, these paths aren't circles at all. That massive breakthrough led to his first and second laws in 1609 and his third law in 1619. Let's move on to part 2, Orbital Mechanics 101. Now, like any good physics class, we need to build our vocabulary first, so we're all speaking the exact same scientific language. First up, orbit. Very simply put, an orbit is the path followed by a planet around the sun. It's literally the track our Earth is running on right now. Next, an ellipse. Honestly, this is just a fancy scientific term for an oval-shaped curve. But as Kepler discovered, this oval is the actual, real-world shape of our planetary paths. And finally, we have a focus. Now, what's really interesting here is the difference between a circle and an ellipse. A circle revolves around one single center point, right? But an ellipse, it actually has 2 fixed internal points called focuses. Keep this in the back of your mind because it's a super crucial detail for what comes next. All right, grab your notebooks. Part 3, Kepler's 3 powerful laws. Class is officially in session for the 3 rules that quite literally changed astronomy forever. The first law is the law of ellipses. It states that every planet moves around the sun in an elliptical orbit, with the sun at one focus. And here's a brilliant way to picture how it works. Imagine stretching a rubber band around 2 pins stuck in a board. The oval shape that rubber band makes, that's an ellipse. Now imagine the sun is sitting right on top of one of those pins. The other pin? It's just empty space. This completely explains exactly why our distance from the sun is constantly changing throughout the year. Let's move to the second law, the law of equal areas. The technical definition says a line joining a planet and the sun sweeps out equal areas during equal intervals of time. But hey, the crucial takeaway here is this. When a planet is closer to the sun, it moves faster. When it's farther away, it moves slower. This completely shattered the old myth that planets just cruise along at one constant, boring speed. Now, if the geometry of that sounds a little abstract, think about this everyday analogy. Picture an ice figure skater. When the skater pulls their arms inward, what happens? They spin much, much faster, right? It's the exact same physics principle. As a planet gets pulled in closer to the sun, it whips around faster, and as it swings out wider, it naturally slows down. Okay, now for the third law, the law of harmonies. Let's bring this over to the digital chalkboard. T squared is proportional to a cubed. T is the orbital period, basically how long a year is in seconds or years, and a is the semi-major axis, which represents the distance from the sun. What this mathematically dictates is just incredibly elegant. Simply put, the farther a planet is from the sun, the longer it takes to complete one orbit. To lock all this foundational knowledge in, here's a quick cheat sheet summarizing the 3 laws. First law, it's all about the elliptical orbit defining the shape. Second law, equal areas and equal time, defining the variable speed. Third law, the time-distance relationship, defining the orbital period. So you have shape, speed, and time, all beautifully and mathematically tied together. Which brings us to part 4,
applications, and myth-busting.
This is the really fun part of the class where we get to look at some mind-blowing numbers, bust a major myth, and see how a 400-year-old math concept is used in our modern world. First number, 29.8. Right now, as you're watching this explainer, you are sitting on a rock that is hurtling through space at a staggering average speed of 29.8 kilometers per second. Just let that sink in.
Now, what about 88? Remember the third law we just talked about? Because the planet Mercury is tucked up so incredibly close to the sun, it zips through its entire year in just 88 Earth days. Literally, by the time Earth celebrates one new year, Mercury has already celebrated 4. But then contrast that with 165. Neptune is so far out on the frigid edge of the solar system that a single orbit, just one Neptunian year, takes a massive 165 Earth years to complete. Crazy, right? All right, let's do a quick pop quiz review to bust the most common mistakes students make. The myth: planetary orbits are perfect circles. The reality: they are actually ellipses. Even if some orbits look nearly circular to the naked eye, geometrically, they are always stretching into ellipses. Now, you might be sitting there wondering, okay, why does this matter to me today? Well, look at these modern, real-world applications. Satellite design, NASA space missions, the very GPS technology sitting in your smartphone right now, and even the discovery of new exoplanets far beyond our reach. These incredible leaps in technology all rely entirely on the exact same physical principles Johannes Kepler published way back in 1609.
And that brings us to part 5, the final takeaway.
Let's bring all these concepts home. Here are the absolute core takeaways that you need to remember. 1. Planets move in elliptical orbits with the sun at one focus. 2. They move faster near the sun and slower farther away. And 3. The length of a planet's year is deeply and mathematically tied to its distance from the sun. It's often said that Kepler's observations remain one of the greatest achievements in the history of science, because what Kepler essentially did was map out how the planets move. He didn't know exactly why they move that way. That actually required Isaac Newton to come along a bit later and explain it all fundamentally with gravity. But Newton absolutely couldn't have mathematically explained gravity without Kepler laying down these brilliant tracks first. So I'll leave you with this final, kind of amazing thought. If Johannes Kepler managed to unlock the fundamental mechanics of our entire solar system purely by analyzing handwritten data points without a single telescope, what distant, unimaginable worlds will these exact same laws help us discover next? Thank you so much for joining me for this explainer. Class dismissed, and as always, keep looking up.